Hello, this is Jason Harrington, and for this section, we're going to do an introduction to differential equations, and we're going to talk about solutions and initial value problems. And this section is primarily definition heavy. So we're going to cover the different forms of differential equations, implicit versus implicit, and we're going to talk about initial value problems, and then we're going to end this particular section with existence and uniqueness. So let's go ahead and begin with the definition of a general form, and then we're going to start with a normal form. So for a general form of an nth order equation with x independent and y independent, basically what this says is that we're going to have a function of x, y, the first derivative, second derivative, all the way up to the nth derivative, and it's going to be equal to 0. And you'll notice that we actually have n plus 2 variables because we have x and y, and then we have all of the derivatives. So these, first derivative, second derivative, all the way up to the nth derivative, has n variables here, and then we're going to have x and y, so that's why we have n plus 2. Now, the most important form that we're going to be using is going to be the normal form, and what we're going to do here is, basically, if you go back and you look at the general form, we're going to just take the nth derivative and then solve for that. And if you take the nth derivative and solve for that, then you're going to get a function of basically n plus 1 variables. So we'll have x, y, the first derivative, all the way up to the n plus 1 derivative. Now the normal form is often preferable, and we'll typically write things like that for the first while. I'm going to start off with an ODE, and in this ODE I'm going to have 3y double prime plus y times y prime plus 5xy is equal to e to the x. Now the highest order is going to be the y double prime. So that's the highest order derivative that we have, and that's what I want to solve for. And so when I solve for that, I'm going to have 3y double prime, and I'm just going to put everything over on the right hand side that is not the double prime. So I have e to the x minus y times y prime minus 5xy. And then now I'm going to divide both sides by 3. And I'm going to have 1/3 e to the x minus y times y prime minus 5xy. And this is what I call my normal form, because I have solved for the highest order derivative. All right, so now let's look at explicit solutions and implicit solutions. So an explicit solution is a function that when substituted for y in the ODE satisfies the equation for all x in the interval I. So basically we have a solution that we can write in terms of x, and implicit is a relation of g of x comma y that's equal to 0. And really the difference here is that we'll see is this one explicitly means we can solve for a function. Like example, we can solve for something like, phi of x is equal to x squared plus x minus 2. That's a nice little function. But implicit will have something that we can't solve exactly for y or x. We'll have maybe x squared plus y cubed times x minus y squared is equal to 2. You see, in this case here, we can't actually solve for y. Cannot solve for y or even x. But this curve may be a solution. But this curve may solve an ODE. We'll do 2 examples of both of those so that we can see it. All right, so let's do the first example. It says, show that phi of x is equal to x squared minus x to the negative 1 is an explicit solution to the linear equation x squared times the second derivative of y with respect to x is equal to twice y. Now really all this is saying is I want to put this function inside the ODE and just ask, does it work? Does this work? And really it's just a yes or no question. Either it does or it doesn't. So I'm going to start off with, I'm going to have phi of x is equal to x squared minus x to the negative 1. The first derivative of phi is equal to 2x plus x to the negative 2. And then the second derivative of phi is just equal to 2 minus 2x to the negative 3. And I'm going to substitute this back into the second derivative and see what happens. So here's how I start this. I just say I'm going to check. And again, I'm going to start on the left-hand side and see if I can end up with what's on the right-hand side. All right, so I have x squared times y double prime, and I'm going to substitute my phi in there and see what happens. So I have x squared times 2 minus 2x to the negative 3. I distribute the x squared to each term, and I get 2x squared minus 2x to the negative 1, which is equal to 2. I can factor out a 2 from both terms, and I'm going to have x squared minus x to the negative 1. And if I look at this, that's actually my original phi function, which is my original, which actually turns into y, so that's going to be equal to 2 times y. So i.e., this x squared times y double prime does in fact equal 2 times y. So it is a solution. Now if it doesn't, then you would say it's not an explicit solution. And here's another one. I want to verify that this function that I have here, once I substitute it inside, the question is, does it work? So again, we do the same thing that we did before. I have phi of x is equal to c sub 1 sine of x plus c sub 2 cosine of x. And I take the first derivative, and the derivative of sine is cosine. So I have c sub 1 times cosine of x minus c sub 2 of sine of x. And then the second derivative is going to equal to negative c1 times sine of x minus c sub 2 times cosine of x. And again, I'm just going to substitute this back into the original equation and see what happens. So now I check, and I have y double prime plus y. Well, if I put that in there, I'm going to have negative c1 sine of x minus c sub 2 cosine of x plus our y, our phi in this case, c sub 1 sine of x plus c sub 2 cosine of x. And you'll see that each one of these terms cancels out, leaving us with 0. So yes, this in fact does work, and it is a solution to the ODE. And what's neat about this is C1 and C2 were arbitrary, so you actually have a whole parameter or a whole family of solutions to this one differential equation. For this next example, I want to verify that x squared plus c times y squared equals 1, where c is an arbitrary non-zero constant, is a one-parameter family of implicit solutions to this particular ODE. Now let's go ahead and get started. Now, unlike explicit solutions, I can't just go around making substitutions. For this one, I have an equation that I want to manipulate to turn it into the ODE. Now, luckily, the ODE gives us some hints. In this example, we have everything in terms of the derivative. So I know that if I start with my solution, and I'm going to have x squared plus y squared, c times y squared is equal to 1, I want to take the derivative of both sides and solve for dy dx. So I'm going to take the derivative of both sides with respect to x and solve for dy over dx. So that's the first thing I'm going to do. So I have, if I take the derivative of both sides, c times y squared is equal to the derivative of 1, and the derivative of 1 is just equal to 0, by the way. That's pretty simple. On the left-hand side, I'm left with the derivative of x squared with respect to x is 2x, and the derivative of y with respect to x, or sorry, y squared, is just going to be c times 2y times the derivative of the inside, which is dy over dx. And that's equal to 0. And this is what I want to solve for, the dy over dx. So let's see what happens. I'm going to have dy over dx. I'm going to have negative 2x. So basically I'm just going to bring over the negative 2 to the right-hand side and then divide everything by 2cy. All right, so I get 2cy. And you'll notice that the 2's cancel out. So now I'm left with dy over dx is equal to negative x divided by cy. Now, that does not look like our ODE, but you'll notice that in the numerator, we have x times y. So maybe if I multiply through by y, I can make it look a little bit better. Also, I want to get rid of this c, right? I don't want any c's in my solutions. There's no c's on the right-hand side. So if I just multiply the top, the numerator, by y, I also must multiply the denominator by y as well. So the numerator becomes negative xy, and the bottom becomes cy squared. All right, now this is looking a lot better, but check this out. If I come over here back to this original problem, notice that cy squared is just equal to 1 minus x squared. Huh, that's pretty cute. So now I'm going to have negative xy, and I'm just going to turn this little guy back into 1 minus x squared. So i.e., I have dy over dx is equal to negative x times y divided by 1 minus x squared. Now that's super close, but there's a negative in the numerator. But if I factor a negative out of the denominator, I get exactly what I want. So thus, I get dy over dx is equal to. And if I factor out the negative in the denominator, I'm going to have x squared minus 1. And that means that the equation that I have works. It's a solution. Now to recap this process, what I do is I start with the equation, and I want to manipulate it into the differential equation. That's what we do for implicit. And you'll notice that this process may be different depending on the equation or the differential equation, and it takes a little bit more thought than just the explicit solution. But I think they're a lot more fun. And speaking of fun, if I look at the last problem, I went ahead and sketched some implicit solutions for different c values. So you see that when I have something like when c is equal to 1, I have this blue solution. That's just a circle. So you see there's my circle. And when you see that I have x squared plus 3, when c is equal to 3, then I have this ellipse. So we can get different solutions. For example, if I have negative 3, you'll notice that now I have two disjoint curves. Actually will satisfy the solution to the ODE. which is kind of neat. By an initial value problem for an nth order difference equation, all we mean is that not only does it solve the difference equation, but then it must also solve some initial conditions, like putting in the original point. If you put the point in for x, you should get y naught. If you put in x naught into the derivative, you should get y sub 1, and so forth. So now you just have to check, does it work for the difference equation, but also does it work for these points as well? So let's try this out. We've already checked to see if phi works as an explicit solution, but you'll notice now we have these initial conditions. So these are the only thing that's really different now, these initial conditions. So let's just check those out. So 1, I'm going to have phi of x is equal to sine of x minus cosine of x. I have the first derivative is going to be equal to cosine of x minus sine of x. Sorry, plus. And then the second derivative of x is going to equal to negative sine of x plus cosine of x. All right, so the first thing I'll do is I'll check the initial value conditions. So I want to check the initial value conditions. And that's typically what I write. So phi of 0 is equal to sine of 0 minus cosine of 0. So that's just 0, and that's negative 1. Okay, so that works. And then I check the first derivative, and that's going to be equal to cosine of 0 plus sine of 0, which also equals 1. So that works. And then, don't forget, you also have to make sure that it satisfies the ODE. So the next question is, does phi of x satisfy the ODE? Let's check it out. Well, we're going to have y double prime plus y. And again, I'm just going to substitute each one of those in there. Phi. So I have phi plus, or the second derivative of phi plus phi is equal to negative sine of x plus cosine of x. That's the second derivative that I'm getting from up here. I'm just putting it into substitution. And then I have plus phi, which is sine of x minus cosine of x. And you should see that everything nicely cancels, giving me 0. So yes, so it does work. So phi is a solution to the initial value problem. And typically, don't forget, I'm going to use IVP for initial value problem. So really the only difference between an initial value problem checking it and the previous part is you have to make sure that the function works with the initial conditions. Now this theorem is probably the most important theorem for all you applied people out there, because if you make a perfect model, and it's a beautiful model, but there's no solution to it, and nothing exists, then it's not really a good model and it doesn't help anybody. So, before you start solving problems, you want to make sure that something exists and that it's unique. In this case, I'm going to consider the initial value problem, the IVP, of dy over dx, so it's a first order linear ODE with one initial condition, so at x naught I get y. Now there's only a couple things you really have to consider. First of all, this function f must be continuous at this point and around this point. And this function, if I take the derivative of f with respect to y, must also be continuous around or near this point. And all this rectangular point means is just that basically, if I look at it, I'm going to start off here at some point. I'm going to have x naught comma y naught. And I want to basically build a rectangle around that point, and I want to just make sure the function is nice and continuous and that the function is differentiable on what with respect to y near that interval. So let's take a look at some examples here. So now I want to check this initial value problem, this IVP, of this differential equations with that particular point. But step one, I have to make sure it looks like the setup of the theorem. So first of all, I'm going to write this as dy over dx, and I'm going to write this as 1/3 x squared minus x times y cubed, which is just going to be equal to 1/3 x squared minus 1/3 x y cubed. So I'm going to let my function f of x comma y, that's this guy. Now the nice thing about this function here is that that's a nice multivariate parabola. So that's nice and continuous everywhere. So that's continuous everywhere. So I don't really have any problems. So the second thing is f is continuous. The third thing I want to check is what about the partial of f with respect to y? Now this is going to be equal to, I want to take the derivative of this, that's just going to be 0. And if I take the derivative of this little guy, that's just going to turn it into minus x times y squared. And again, that's also continuous everywhere. Let alone any rectangular solution. So yes. So this initial value problem has a unique solution. Because really any point 1, 0, right, the function and the second derivative with respect to y, or the partial derivative of f with respect to y, is continuous everywhere. So that's not an issue. Now let's take a look at this particular initial value problem, IVP. So for this one, it's already set up. So 1, we're going to have f of x comma y. We already have it in the terms where we have the dy over dx is already isolated. So this is just going to be y to the 2/3. All right, so that is, so note here that f is continuous everywhere. So that's not a problem because I'm taking the cube root and then I'm squaring it. Third, if I look at the partial of f with respect to y, what's going to happen here is that I'm going to have 3 times 2/3 y to the negative 1/3. So now I'm going to have 2 y to the negative 1/3. And if I write that out, so that's going to be 2 divided by the cube root of y. Now note, that is going to be a problem. So note, y cannot be equal to 0. It causes division by 0. And if you look up at here, you're going to say, oh no, my initial condition is, y of 2 is equal to 0. And since y sub 2 is equal to 0, so i.e. the point goes through 2 comma 0, causes problems for partial of f with respect to y, we are not guaranteed a unique solution. Now again, I don't know what happens, right? There still could be a unique solution. We're just not guaranteed one, right? There could be other solutions. There could be, maybe a solution doesn't exist. Maybe one does. I literally don't really know. The theorem only says, if these conditions are met, I know for a fact I'm going to get a unique solution. If the conditions are not met, I don't know. May or may not get a unique solution. Now, this looks just like the similar problem from before, except now the only difference is that I changed the initial value condition. And check this out. 1, I have f of x comma y is equal to 3y to the 2/3, just like before. 2, f is continuous everywhere, just like before. But this time, 3, the partial of f with respect to y, just like before, I'm going to have equal to 2 divided by the cube root of y. But this is continuous when y does not equal to 0. And in this case, we're okay. Now this also tells us how close we can be, right? So now I'm going to have to pick my rectangle to get my unique solution, R. X can really be anything. That's fine. X doesn't really matter. So I can say X is between, say, 0 and 10. That doesn't really matter. I just picked some numbers there. But the smallest the y value can be is 0. It can't actually become 0. It has to be bigger than 0. And again, I'm just going to cap it off somewhere at 5 or somewhere else. It doesn't really matter. So the numbers I have in red, I sort of just made up to make an interval, to make a rectangle. As long as this is away from 0, I'm okay. Right? It'll work. So the answer in this case is yes. This does have a unique solution. This ODE with initial value conditions has a unique solution, which is pretty neat.